Hello friends, fellow modelers and aviation enthusiasts. For my next big project, I wanted to tackle a build that would be a good challenge, but also provide a really valuable and detailed guide. After a lot of thought, I've chosen the Spacewalker 2. This plane has won the hearts of modelers everywhere, and it's easy to see why. Its excellent flight characteristics and harmonious design make it a perfect subject for a scale model, especially at a larger size. So, why did I decide on a 1:2 scale? While there are plenty of plans and kits available in smaller sizes, I wanted to do something unique. The half scale was also incredibly straightforward to work with. All I had to do was take the dimensions of the real aircraft and divide them by 2. Besides the math, I've always loved building large models. Their construction can be very similar to that of a full-size aircraft. This was a demanding task that required precise planning, detailed drawings, and thoughtful construction. It was a build that truly tested my skills, but the end result is a design of a majestic, airworthy model and an immense sense of satisfaction. In this video, I want to show you how I digitally designed the plan for the Spacewalker 2 in an Autodesk program called Fusion. I shall walk you through every step of the construction, from the basic outlines all the way to the detailed construction. I'll also share the strategies I used to design a strong yet lightweight structure, and how to avoid common construction errors that could have jeopardized a build this challenging. My ultimate goal was to create a complete and accurate plan that could serve as the perfect foundation for building your own impressive Spacewalker 2. This plan is the most advanced one I've created so far. I created 2 different painting color schemes and a full reference surface model, which was the foundation for designing every single structural part. And of course I added full animations. I animated all the moving components, from the propeller to the servos controlling the throttle, choke, ailerons, elevator, and rudder. I also included animations for all the detachable units, like the wings and tail surfaces. One of the challenges was designing the main landing gear. I was able to include functional, compressible damping springs, which was a tough but rewarding feature to get right. The drawings themselves are incredibly detailed. I organized every single component hierarchically using a browser tree structure. But the real game changer is the unique code I gave to every part. I even included it as a sketch right on the plywood components themselves. This makes it incredibly easy to identify and assemble each piece, so you're never left guessing what goes where. You can also turn these codes on or off in the display menu. The best part? They're specifically designed to be burned or milled directly onto each part during production, which makes the entire assembly process unbelievably smooth. And when you're working with the plans, navigating is a breeze. It's easy to find a part in the browser or click on a component in the main window to find it instantly. I designed the entire model as an assembly of components made from lightweight 3mm plywood and fiberglass laminate, with just a few components made from 4mm and 1mm plywood. For the landing gear, I used 2mm thick steel along with steel tubes that had a 1mm wall thickness. And for other critical components, like the wing and tail connecting tubes and the tailwheel leg, I chose duralumin. This combination of materials allowed me to create a strong yet incredibly lightweight and durable model. The completed model design has an impressive wingspan of around 4.25 meters, and it's powered by a 280 cubic centimeter 4-stroke 4-cylinder gasoline engine. This model could have been easily powered by a smaller engine. But for me, the choice was obvious. The fact that it's a 4-cylinder, just like the original aircraft, made it my #1 choice for a realistic build. My design process began with me creating a reference model using surface modeling techniques. I used several canvases with photos and diagrams I found online. I hope I'm not breaking any rules showing them here, as the original reference images are shown in the video. Once the reference model was complete, I divided it into sections to develop the paint design, assigning a distinct color to each part. And for those of you who might want to dig deeper into the plans, I've left all the original sketches and construction items I used during the design process. For the initial reference and paint designs, I kept the design history active, which is a great feature for making quick changes. But once I moved on to the detailed construction, I removed that history to keep the file clean and manageable. You'll notice that the reference and paint designs overlap, so for clarity, I recommend displaying only one at a time. This makes it much easier to see the different details. The actual wooden construction is offset from the painting designs by about 0.5 millimeter. This creates a perfect impression of the paint on the finished model. As we are navigating the design, you might notice something interesting. From certain angles, you can see the internal components right through the surface model. As you zoom in for a closer look, that transparency, however, disappears. I organize the entire design in a browser tree format, which makes it incredibly easy to navigate. The entire model is broken down into a hierarchical structure, with separate sub-assemblies for key components like the fuselage, wings, and stabilizers. This breakdown continues to the lowest level. For example, the fuselage sub-assembly is further divided into logical subunits like the main board. I included every single part, down to the servo arms, screws, and nuts. Just like a real model, this digital design includes all the moving parts, so you can see exactly how everything fits together and operates before you even start building. Now let's take a closer look at the construction design itself. The construction uses traditional plywood parts assembled together. The rear section of the fuselage has a structure made from 10 by 10 millimeter spruce spars. The assembly begins with the bottom of the fuselage, which is built on a flat surface with the upper side facing down. To make the build process incredibly easy, I numbered all the components in the browser tree in the exact order they should be assembled. For example, all the fuselage parts start with F, followed by a number indicating the sequence. I'll show you exactly how this works now. I hid all the components in the design, and I'll reveal them one by one in the correct order, just like you would during the actual build. The assembly begins with the motor box, starting with the main firewall, labeled F1. Next, all the side, top, and bottom formers, from F2 to F5, are added to create the motorbox structure. The firewall is then reinforced by inserting parts F6 and F7. This completes the motorbox assembly, and we can then set it aside to be used later in the build. The fuselage assembly starts with the longest part of the entire model, the fuselage main board, which is almost 2,300 millimeters long. The board is placed upside down on a flat working surface to begin the build. As mentioned before, I created an automatic labeling system for all the parts. Each component has its own short, easy-to-read label that's automatically generated from the component's full name in the browser tree. I was able to do this with a custom script originally written by Brian Ekins, which I slightly modified to break the label at first space character of the component name. It takes just a few seconds to run, and if I ever changed a component's name, the label would update after I ran the script again. It was a huge help in keeping everything organized and easy to find. Following the browser tree, we are gluing the individual components one by one, starting with the 10 by 10 millimeter spruce spars. These spars are forming the basis for the entire fuselage. Next, we are adding the fuselage formers. Their tenons fit perfectly into the mortises on the main board. Here's another smart detail in the plans. You'll notice the former names include a capital letter, like E. This letter corresponds to a specific cross-section that was defined during the initial design, and you can still find these construction planes in the browser tree. This system allows you to easily find the exact location of each former and understand its relationship to the overall shape of the fuselage. With the formers in place, we are now adding both fuselage sides, followed by the fuselage board bottom and the landing gear reinforcements. Here's a critical step. I'm recommending you insert the T-nut inserts at this point, because they will be extremely difficult to access later on. The entire process is designed so every component fits easily, but changing the order could make it difficult to insert other parts later. The first major phase of this build ends with component F65. Now, we are turning the entire assembly of the fuselage top side up. With the assembly flipped, we can now glue in the already assembled motor box. Then we continue with the assembly of the upper part of the fuselage. We insert and glue the fuselage formers in their respective positions, starting with F66 and continuing all the way to F78. Here's an important step. We need to insert the servo cable duct tube now, because it will be impossible to do later. With that in place, we insert the vertical stabilizer mainboard, F80, followed by the last fuselage former F81 and reinforcement F82. The top rear fuselage section is then completed by adding the spruce spars and balsa shapers. Now we are returning to the bottom section of the fuselage to work on the wings center section. Starting with component F85, we are inserting the root ribs of the wings. These ribs are doubled for a very important reason. They provide the extra strength needed right at the wing root. Here's a very important note for anyone following these plans. You'll notice that some components, like these two ribs, F87 and F88, look almost identical. However, if you look closely, you can see they are slightly different. This is because of the wing's dihedral. The holes for the joining tubes are at a different height in each rib. The difference is only a few tenths of a millimeter, but swapping these parts, or any others throughout the model, might cause assembly problems later on. So always double-check your component labels. Now, we're adding a variety of other components to the assembly, like joining tube sleeves, cable ducts, and wing and landing gear holders. An important thing to note is that the main flow of steps in the browser tree doesn't necessarily include every single component. If I included every screw, washer, and nut in the main numbered list, it would become incredibly long and difficult to navigate. Instead, these smaller hardware items are organized in separate directories. So, when you're ready to install the landing gear, you'll find all the necessary screws and nuts in the landing gear, screws and nuts directory. This keeps the main build process clear and focused. With the assembly complete, we are now ready to apply the balsa wood fuselage sheeting, which covers mainly the front half of the fuselage. After that, we need to add the wing root or center rib sheeting. This is a crucial step that must be done meticulously, as the sheeting has to be perfectly aligned with the wing's dihedral. This attention to detail ensures a flawless and seamless transition from the fuselage to the wings. We are now finishing the assembly of the fuselage rear end by adding the remaining numbered components. The numbered list ends with component F118, which is the vertical stabilizer reinforcement. From here on, the order of individual components is no longer critical. However, a very important detail to note is that the multiplex connector for the elevator servos is glued in place at a slight angle. This is because of the tapering shape of the rear fuselage and the way the joining tubes intersect it. This becomes much more apparent when we demonstrate the horizontal stabilizer disassembly. The fuselage assembly also includes the motor cowl, which is designed to be made from fiberglass. The cool thing is, you can use the digital component to create either a positive or a negative mold for the actual fiberglass part. Just a quick note. The actual mold design isn't part of these drawings. The front and rear windshields are also included in the assembly and are designed to be made from a transparent plastic like AXPET or Vivac. That completes the fuselage assembly for now. We are now moving on to the next section, which is the rudder assembly. The rudder assembly is quite simple and straightforward. It consists of a rudder main board with balsa wood reinforcement and fiberglass control arms. The hinges we are using are the standard large Robart hinges. Here's a key tip for a perfect assembly. I suggest you drill the holes for the hinges into the balsa reinforcement after you've glued the reinforcement in place. Use the holes in the plywood as a guideline for your drill bit. This ensures all your hinge holes are perfectly aligned. The design for the landing gear follows the concept used on the real Spacewalker, with both outer and inner shock absorber springs to absorb shocks, especially during landing. For demonstration purposes, only the outer spring is designed to be functional. Making the inner spring fully functional in the drawing would have made the assembly too complicated with little benefit for showing the functionality. The joints for the landing gear legs have a defined 0 position, so they automatically return to their proper place. The main landing gear is designed to be made from steel tubes that are hard brassed together. The sheeting for the main legs, or the wheel pants, is designed to be made from fiberglass. You can use the digital components for the pants as a basis for creating either a positive or a negative mold. Now let's move on to the horizontal stabilizer and elevator. A great feature of this design is that both halves of the horizontal tail surfaces are removable from the fuselage for easy transportation. To do this, you just need to unscrew 4 screws that fix the tail struts in place, as you can see in this animation. There's an important design detail to note here. The combined thickness of the elevator and stabilizer, including the covering, is about 12 millimeters, while the servos we're using are 20 millimeters thick. This means the servos will protrude from the bottom by about 8 millimeters. I've designed the servos to be in the elevator itself, because it's much easier to disconnect a servo connector than to disassemble a servo pushrod every time you want to transport the model. The alternative of installing the servos in the fuselage would require you to take apart that pushrod for every transport, and that's a much bigger hassle. To properly demonstrate the servo controls for the elevator, we are pinning the horizontal stabilizer in place. In terms of construction, both the horizontal stabilizer and the elevator are very simple, similar to how we built the rudder. The basis of the horizontal stabilizer is the main board. As with the other assemblies, it's recommended to follow the component order given in the browser. The servos are mounted in removable servo holders that are secured with just 2 screws per servo. Just a quick note. We are not demonstrating the servo removal here, because animating the elevator control, disassembly and servo removal all at once would make the drawing overly complicated. The small holes in the main board are for guiding the servo cables. You must insert these cables before you do any covering, as it will be almost impossible to do afterwards. The multiplex connector is glued in at an angle. I suggest you glue both the connector in the stabilizer and the one in the fuselage at the same time to ensure a perfect fit. The construction of the elevator is very simple. It's just a main board with balsa wood reinforcement and control horns. Both the left and right sides are identical, just mirrored. The struts are equipped with turnbuckles, which allow you to precisely adjust the stabilizer's position and the tension of the struts, ensuring a perfect setup. Now let's take a quick look at the motor assembly. The motor is mounted on 4 duralumin spacers that are attached to the firewall with 4 screws, washers, and T-nut inserts. The throttle and choke servos are mounted on the front former as close to the carburetor as possible for a direct and responsive link. The silencer is a simple muffler. For the propeller, we are using the recommended size of 36 by 14 inches. The digital model of the spinner can be used for making a mold, but I believe a similar product can also be sourced commercially. The ignition is not included in the drawings, but there is plenty of space to mount it. A possible location is on the side of the motor box on the front former, which would depend on the length of your ignition cables. The rudder servos are installed in the front cockpit and are linked together with push rods. The rudder and similarly the rear wheel's control arm, are operated using a pull wire system. This setup provides a lightweight and direct control linkage for both the rudder and the tail wheel. Last but not least, let's look at the wings. The wings are inserted onto the joining tubes and held to the fuselage by a single screw on each side. To show the disassembly, I'm unpinning the sheeting on the left wing panel. Just like the elevator, both aileron servos are connected to the RC equipment in the fuselage using multiplex connectors. The servo cables run through fiberglass ducts. These ducts are shown as transparent for this demonstration to give you a clear view of how they are placed within the wings. Now we are starting the wing assembly. I recommend following the numbering order in the browser for easy assembly, which begins with the two main spar webs and the front web's reinforcement. A very important note. The wing's joining tube has a maximum diameter of 50 millimeters. Because each wing has a 4-degree dihedral, the amount of material in the spar web around the tube opening is very small, less than 4 millimeters. This makes the web easy to break, but don't worry. This is not a big problem, as the web is primarily there to keep the distance between the top and bottom spruce spars and to transfer forces. After the webs are in place, we insert the ribs, starting from the root rib and moving to the tip rib. You'll notice there are 4 rib reinforcements between the main 2 root ribs. This is to reinforce the connection of the wing panels to the fuselage where the fixing screw goes in. Now we are adding 2 servo boxes to the wing, which fit between ribs 18 and 20 and 22 and 24. You can also notice that the rib numbers and other wing components are preceded by a prefix. This is a great feature that makes it easy to keep track of the parts. WR stands for right wing and WL stands for left wing. You'll notice that the servo box component, number 19, doesn't show a material. That's because it's a sub-assembly that contains all the individual parts for the servo box. To see the components, you just need to open the sub-assembly in the browser tree. This is how all 4 of the servo boxes are organized, and it's a good thing to remember, as other parts of the design are also organized this way to keep the main view clean and manageable. Next, we insert the aileron hinges into their positions. Since they are all the same, they have the same number in the browser tree. After that, we glue 4 spruce spars to the ribs and webs. At this point, it's critical to make sure the wing is perfectly straight. We are placing the wing on a straight desk and supporting it with some bars to keep it level. A mistake here can lead to a crooked wing, which is something we want to avoid at all costs. You'll need to keep the wing straight during the entire build until the final balsa sheeting is applied. The rear top and bottom spars lock the aileron hinges in place, and we complete the basic construction by adding the leading spruce spar and the balsa leading and trailing edges. We then insert the front and rear joining tube sleeves, followed by the servos and lighting cable ducts. The wingtip arc is added along with its reinforcement. This reinforcement is very important. It acts as a strong support when you are later covering the wing with a material like seconite, which can generate powerful forces when you iron it on. The wingtip arc is also provided with top and bottom balsa wood tips to help shape the ends perfectly. We are now gluing 4 servo holder reinforcements to the servo boxes in each wing panel. We also reinforce the 2 standalone aileron hinges with side-by-side triangle pieces of balsa wood. Next, we insert the T-nut inserts for both the servo mounts and the wing panel fixing screw. Now it's time for the final balsa sheeting. While the servos are shown here, it's best to install them after the wing is covered and painted. Now that we've finished the wing panels, it's time to proceed with the ailerons. Their construction is very simple and straightforward. We start with the main board and then add the aileron main spar and all the plywood ribs. After that, we add the trailing and leading edges, along with the ribs that hold the hinges and the fiberglass control arms. The aileron construction is then completed with balsa wood sheeting. Well, that basically concludes the design and construction of the Spacewalker model. What remains now is covering and painting. For a model of this size, I highly recommend using Seconite for the covering, as a plastic film just doesn't provide the right impression. As I have mentioned earlier, the vast majority of the parts are made from 3mm thick poplar plywood. We're also using 3mm thick glass fibre for some components, like the hinge and control arms. Just a few other parts are made from 1 and 4mm thick plywood. To simplify the build, I've prepared arrangements of most of the parts needed for CNC cutting. The arrangements are sized for a 1100 by 2300mm CNC machine table, but you can export the plans as a DXF file and rearrange them to suit your needs. You can also rearrange the parts within the Fusion drawing itself. To make the CNC cutting process as smooth as possible, I've created all the necessary machine paths for every single part. These paths are organized into multiple setups and operations, with one complete setup for each arrangement envelope. This way, you can easily load each sheet into your machine and run the corresponding setup. Please note that the very first operation in each setup engraves the component label directly onto the part itself. This makes the identification of every part incredibly easy. The engraving, along with the fact that some parts are very small and thin, makes a laser cutter a potentially better option than a milling machine for this model. The simulation shows that the milling process is designed to support nested parts, starting with the internal contours and then moving to the external contours. We achieve this by carefully selecting the cutting paths in the correct sequence and using the preserve order option in the 2D contour milling operation. For milling, we are using a 1-flute, 1.6mm flat-end mill. The parameters are set to 10,000 RPM and a speed of 600 mm per minute for plywood, but these should be modified to suit your specific needs and machine. Well, that wraps up our detailed walkthrough of the Spacewalker 2 design. Thanks so much for watching. Your support means a lot, and I hope this video helps ignite your own passion for building. If you have any questions or just want to share your thoughts, feel free to drop a comment below. I'd love to hear from you. Until next time, happy building.